Good afternoon to all present here. I request you all to turn off your mic and your video and on your camera, and please don't present your screen, professors. I'm repeating, dear professors, please turn on your mic and your camera, and please don't present in between while the resource person is presenting his or her screen. Thank you. Professor Nisha NR, kindly stop your presenting your screen. Dear professors, on behalf of the organizing committee, we request you to turn on your mic and your camera, and please stop presenting your screen. And Professor Ranjita, kindly turn off your mic. And Professor Nisha, kindly turn off your presentation. And it's my pleasure, and I'm delighted to welcome Professor Syed Raumi and Professor Madeline and Professor Agboola and other dignitaries for today's session. We'll start the program shortly. Geeta ma'am, shall we start the session?
Yes, Kartika.
Sir.
Good afternoon to one and all. And today we have the fourth day of the International Faculty Development Program. And today we have the resource person, Professor Agboola, and who has done his master's degree at University of Lagos. Then he entered into Engineering Analysis Unit, Faculty of Engineering, University of Lagos, for his doctoral program in Applied Mathematics, especially in Fluid Dynamics. But however, his PhD was eventually completed in Pure Mathematics. He had published 50 research papers in national and international journals. He has supervised over 25 MScs and 15 doctoral theses in mathematics and mathematical sciences. He has been an external examiner to undergraduate and postgraduate programs in mathematics in Nigeria and abroad. In addition to his contribution to teaching and research, Professor Agboola has rendered the following services within the university system. He was been the member University Governing Council from 2016 to till date, and he has also been the Director Information Communication Technology Resource Center from 2017 to till date. And he has also been a member University Budget Monitoring Committee from 2015 to till date. And he is again a member Senate Coordinating Committee on Examination Results from 2010 onwards. And he's also a member Senate nominee on the college committees on examination results and member University Senate from 2011 onwards. Due to his research and contributions to the development of nutrosophic theory, Professor Agboola was chosen in July 5th, 2015 by International Association of Paradoxisms, a Avant-garde movement in arts and science for distinguished achievement in paradoxism and was conferred with the honorary membership. He was being acting dean, a College of Natural and Applied Sciences, Crescent University, from 2007 March to July, and he has also been a deputy dean, College of Natural and Applied Sciences, Crescent University, from Jan 2006 to March 2007. And Professor Agboola is a reviewer to many local and international journals, including Nigerian Journal and Mathematical Society, American Journal of Mathematics Society, Nutrosophic Sets and Systems, International Journal of Nutrosophic Science. He has also been a member of the following learned societies like Nigerian Mathematical Society, Nigerian Mathematical Association, Science Association of Nigeria, American Mathematical Society, International Association of Paradoxisms, Avant-garde movement in arts and science, and finally he is also a member in Nutrosophic Science International Association. So now I request the professor to take this platform and give his inputs for our participants. May I welcome you too, sir.
Well, thank you very much. Good day to you all. It is my pleasure to be here to present my talk titled The New Trends in Nutrosophic Algebraic Structures and Hyperstructures. The abstract of the paper is, the objective of this paper is to present new trends in nutrosophic algebraic structures and hyperstructures. New research areas in nutrosophic algebraic structures and hyperstructures are also presented. Then I start with the classical algebraic structures. What do you mean by the classical algebraic structure? A classical algebraic structure is a non-empty set X, which we call, of course, the universe of discourse, with one or two more binary operations defined on it. And the name you call such a structure will be determined by the properties or the axioms satisfied by those binary operations defined on the set. And some of the well-known classical algebraic structures are groupoids, semi-groups, monoids, groups, loops, rings, fields, integral domains, module, and vector spaces, and others. And one must have seen here that for the classical algebraic structures, once a particular law is defined on a particular set, all the law will be holding 100% within that particular structure. For example, if you are looking at the axiom of associativity, commutativity, distributivity, all these axioms, they hold within the classical algebraic structures. So for the classical algebraic structures, you have those binary operations, those properties I've mentioned, of course, now will be holding 100%. And one of The example that I'm giving here now is that if we take H to be a normal subgroup of the group G, and we define a mapping phi taking G to G factor by H, defined by phi of X is equals to X plus H. I mean X star H for all X in G. Then we can show that this is actually a group homomorphism. And a homomorphism, of course, now is very key in the study of the classical algebraic structures, because if a map is defined on a classical algebraic structure and it preserves the operation of, on that particular structure, then such a map, of course, now is called, a homomorphism. And one of such examples is what I've just given here. That if you consider G to be a group and you take H now to be his normal subgroup, and you define a map phi taking G now to G factor by H, defined by phi of X is equals to X star H for all X in G, then it can be shown that such a map, preserves the operation that you have defined there. So it's a homomorphism. Also, another good example is that if you take G now to be an ideal of a ring, the mapping psi, taking R to R factor by J, where J is the ideal, and is defined by psi of X is equals to X plus J for all X in R, then it can equally be shown that this is also a homomorphism. So for the classical structures, so we have all that. But for the purpose of this particular talk or lecture, we want to talk about the nitrosofic algebraic structures. You see, in the classical structures, as I said earlier, all the laws defined, the axioms defined, they are all true. For example, the commutativity, associativity, distributivity, they are all true, But in the real sense of it, this is not the real situation. And therefore, in 1995, Professor Smandache, brought in a new, philosophy, which of course now he called the nitrosofic philosophy. So I would not want to, deal with all that, because the Professor Salama yesterday, of course, now introduced us to the nitrosofic logic, and gave us all the applications. I will not want to, repeat all that. I will just go straight away now into nitrosofic algebraic structures. Now, what do you call a nitrosofic algebraic structure? If you consider a particular structure, call it X star, let it be any classical algebraic structure. We can generate a nitrosofic algebraic structure now from it, by having a set, which of course we called NX or XI. So, which of course we write as X union I, where I is the indeterminate factor. So we have this, and that's a set, of course, now X union I is defined as the set of A, BI, such that AB is in X, and I is called the nitrosofic element, and it has the property that is, if you add I plus I in n places, then you have Ni. If you multiply I with 0, then you have 0. Then you raise I now to the power of n, you get I for all n in the set of natural number. But one thing is very key here, that the inverse of I is not defined, and therefore it doesn't exist. Okay, so when you now when you generate a structure from X, along with I, then you must have generated what we term in nitrosofic algebraic structure. And as I said now in this the same thing, of course, now for the classical case, the name we are going to give to that particular structure will be the name from the parent set. If X is standing for a group, then our new structure, of course, now will be called the nitrosofic group. If it's a ring, it will be called in the isosophic ring. And if it's any other tail, of course, now the name, of course, now will be derived now from the parent structure. And again, just like we have in the classical sense, if you have an isosophic algebraic structure, and we have a map defined on it, which preserves the binary operation of that particular structure, then such a map is called in isosophic a map, because it preserves the binary operation of the structure. All right, and you know, so many, since the introduction of this particular algebra structure that by Smarandache and Kadasame, I mean, some years back, many people have worked in this area of mathematics, myself and some other people, and we have, you know, come up with several isosophic algebraic structures, and some of which are, you know, isosophic groupoids, isosophic semi-groups, monoids, isosophic groups, isosophic loops, isosophic rings, isosophic fields, isosophic integral domains. And you can see the examples that I've given there, and also the isosophic modules, and probably the isosophic vector spaces. I have worked in you know, in most of these structures. We have established, you know, many of their properties, and they are available in the literature. So I now move now to the refined isosophic algebraic structures. All right. So having introduced the element I, which you call the indeterminacy, you know, factor, you know, Smarandache recently, of course, now introduced the notion of the refined the refined structure, whereby, of course, now we can split the indeterminacy factor I into two or more, you know, indeterminacies, you know. But for the sake of this presentation, I will look at the situation whereby I is split into two, okay, into two. So I1 and I2, that is, we split the indeterminate factor, of course, now into two indeterminacies. So we have I1 and we have I2. So I1 in this case, of course, now is standing up for contradiction. That is the situation whereby we have a true case and false case. Again, we have I2, which of course now is standing up for the case where we have the situation whereby we have a true value or a false value. Okay, and then we also try now to generate, yes, so we also try now to generate an algebraic structure. So given all these, given these two indeterminacies, I1 and I2, okay, and we say that if you allow X now to be, you know, a non-empty set, and we allow I1 and I2 now to be two indeterminacies, as I've just enumerated, then we can have a structure xi1 I2, which is given now by the set of x, y, I1, z, I2, such that x, y, z is from X, you know. So this particular structure that we have just, you know, obtained is called a refined, it's called a refined isosophic structure, you know, generated now by X, I1 and I2 under the same binary operation, you know, inherited now from the parent set X. All right, and then we go ahead now to say that if the binary operation, if it is just ordinary addition and that of the multiplication, then we can see how the elements can be combined, they can be composed. Okay, so if you have two elements from that particular set, AB1, ABI1, CI1, DEI1, FI2, this from X, I1, I2, then they can be composed. They can be composed by what you have in equation 7, that is AB1, ABI1, CI2 plus DE1 and I1 plus FI2. When you combine this, of course, now you have A plus D, that is the non-isosophic part, and we have the other side, you have a B plus EI1, then C plus FI2. And when you are multiplying, then you have AD, comma, AE plus BD plus BE plus BF plus CEI1. Then you have AF plus CD plus CFI2. Okay, so with this one, then we can generate a structure, which of course now we call the refined philosophical algebraic structure. So what you have just, I've just said in a nutshell is that what you have a structure X, and you do, I mean, you break down the indeterminacy factor I into two, I1 and I2 as defined above, and you now generate a new structure. You call it, XI1, I2. Okay, so with that one, of course, now you have a new structure, and you can combine the elements to the, there. If the binary operation star, of course, now is just of that addition or multiplication, the usual one, then they can be combined the way I've just mentioned. Again, we also try now to define, to look at the homomorphism, that is a map that can preserve the binary operations, defined on X, I1, I2. If you have such a map that preserves the binary operation and at the same time also preserves I1 and I2, then we refer to such a map as a homomorphism. And that is what you have there, that's the phi of AB I1 C I2 star D E I1 comma F I2 is equal to what you have on the right hand side, which of course now is showing the that the map is actually preserving the binary operations defined on X I1 I2 and Y I1 I2. Again, this is very important because you can see the very first property is that of the classical case, but that's what we usually have in the classical algebraic structure. But for this new structure, the phi also must preserve I. So in this case now, phi of ik is equal to ik for all the elements you pick now from xi1, I2, where k is equals to 1, 1, 2. So in this case now, if you have such a map that preserves the binary operation and also preserves the indeterminacies and the factors like I1, I2, then we refer to such a map as a refined philosophic homomorphism. Okay, because it preserves the operations and it also preserves the indeterminacies factor, ik. In this case now, I1 and I2. But we should note that, for either the philosophic algebraic structures or the refined philosophic algebraic structures, the properties, being obeyed in the parent structure might not necessarily be, of course, not be obeyed in this particular structure. If you look at some of our papers, at least that we have shown all that. For example, you can see that, of course, now in the classical group, we may have the Lagrange's theorem, being obeyed. That it is a known fact that what the order of a subgroup divides the order of a group, but that may not happen in the philosophic sense. We have seen that, where of course now we have in the philosophic subgroup whose order does not divide the order of the philosophic group or refined group, as the case may be. So what I'm saying is that there are some properties that may be holding, of course, in the parent structure, which of course now will not hold in the either the philosophic algebraic structures or refined philosophic algebraic structures. And some of the structures that we have established, in the literature, which of course now can be found out, is about the refined philosophic groupoids, refined philosophic semigroups, refined philosophic monoids, refined philosophic groups, loops, rings, fields, integral domains, modules, and vector spaces. All these can be found, in the literature, which of course now we have worked on all this, And then again, I now move now into the philosophical algebraic, hyperstructures. We know in the classical hyperstructures, for the classical non-hyperstructures, if you combine two elements together, okay, you get another element which is in the set. But for the case of the hyperstructures, when you combine two elements together, it produces, it's a set, because we are dealing, of course, now you are moving out, we are considering all the elements have been taken out from the power set of that particular structure. So in this case, we have also said that if you allow H star to any algebraic hyperstructure, what we have done, of course, now is to generate, a nitrosophilic structure from that particular classical structure, which of course now is H star. So in this case, of course, now we say, you have H union I, which of course now is like we are generating, a new structure from H and I, okay, which is defined as the set of XABI such that AB is in H, okay, and this couple H union I then comma star is what is called the nitrosophilic algebraic structure generated by H and I under the hyper operation star. Okay, and the name we give to this new structure, of course, now will be, will be coined from the name from the parent cell, the parent structure. So if the parent structure, of course, now is an hyper group, then what you have just done, of course, now is to have a nitrosophilic hyper group. If the parent structure is hyper ring, then with this generation, you must have gotten, nitrosophilic hyper ring, and so on and so forth like that. Okay, and from this thing you have seen here, that I've mentioned that the other time, that the part A in this this particular set, is called the non-nitrosophilic part of X, and B is called the nitrosophilic part of X. And you can see how we can compose the elements in this new structure. That is, if X is equals to ABI and Y is taken as a CDI, any two arbitrary elements, of course, now from HI. So where A, B, C, D, are elements, of course, now in H, then we can compose X and Y, that's X star Y, to give us ABI star CDI. And this is what you have. And you have to be very careful here because we are dealing with an hyper structure. Okay, so this one will give us, of course, now the set of the elements UVI such that U is in A star C, V is in A star D plus, union, because because A star D, all these operations we see here when we generate a set and not just an element, and that's the reason why in this case we are using the union. That is, V, of course, now is taken out from A star D union B star C union B star D, and then so you now have the set, you have this as A star C. A star C, of course, now is going to be a set, and A star D union B star C, and so on and so forth like that. All these are set, and we said you should note that A star C is a set contained in H, and then A star D union B star C union B star D is also a set contained in H. And some of the structure that we have established, since we started the research, in this particular field, are the following. We have been able to, of course, now to establish, to generate, nitrosophilic, hypergroups, nitrosophilic hyperrings, nitrosophilic hypervector spaces, nitrosophilic hypermodules, nitrosophilic hypergroups, nitrosophilic hyperrings, hypervector spaces, nitrosophilic hypermodules, and nitrosophilic quadruple hypervector spaces. All these, myself and some other researchers, of course, now we have really worked on, and then we have a plenty of literature available now for the viewers, of course, now to look at. Of course, now at the end of this paper, you see the references where people, of course, now can learn more about this. Now, the more importantly is the next section of this paper, which is now called the neutral algebraic structures and anti-algebraic structures. Okay, this is very, very important, and this is in fact, this is the new direction we are talking about. So with respect to the title of the paper, this is the new direction. You will see that, as I said earlier, in the classical algebraic structure, if you are looking for a group, if you are taking a group, for example, you have a group G, and the binary operation is star. That star that is being defined on G is, in the classical sense, of course, now is sacrosanct. Is true for all the elements. Okay, so all the elements, if you are talking about the closure law, then all the elements, of course, now if you combine two elements, of course, now it must be closed. There is no room for non-closure. There's no room for partial closure or non-closure at all. So, and you can see in the real sense, you know, it does that one, of course, if you want to model the real situation, that cannot model the real situation, you know, and that's the reason why I said that in any classical algebraic structure X star, the law of composition of the element of X, otherwise called the binary operation star, is well defined for all the elements of X. That is, for all the elements X, Y you pick from X, X star Y is always in X. But this is not the case in the real sense of it. And axioms like associativity, commutativity, distributivity, and so on, defined on X with respect to star, are totally true for all the elements of X. So what we are saying here is that what, for all the elements of X, that law, you know, those axioms, of course, now are they are true. There is no room for, you know, anti-operation. There's no room for, you know, some elements, of course, now obeying some laws, whereas some elements are not, you know, obeying some laws. And you can see that in the reality, this is the real situation, you know. So in trying to do all that, I said the composition of elements of X this way is restrictive, which does not reflect reality. It does not give room for composition that's either partially defined or partially undefined or totally undefined with respect to star. However, in the domain of knowledge, science, and reality, the law of composition and axiom defined on X may either be only partially defined, partially true, or partially undefined, that is partially false, or totally undefined or totally false with respect to star. So this is exactly what, of course, now it happens in the reality. Okay, and in trying to model the reality, then Spanadache, you know, in 2019, now make an attempt now to factor in all the anomalies, you know, in the classical structure, and you now have situation whereby the Spanadache, of course, now introduce the notion of neutral-defined and anti-defined laws. That is, some laws that, you know, that are either true, you know, false, partially true, partially false, or totally false completely. So as you can see, so you can now, I mean, there's now room now for laws not to be anti-defined, neutral-defined. Neutral-defined means that what? That is, it is partially true and partially false. And anti-defined laws means that what? Laws that are completely, you know, false, you know, in its entirety. So, and you now have, you know, notions of neutral axiom, anti-axiom, which has given, you know, the birth now to new phase of research, which we now called neutral structures, anti-structures, neutral algebras, and anti-algebras. You know, for any classical algebraic law or axiom defined on X, there corresponds neutrosophic triplets, you know, law, neutral law, and anti-law. So for the axiom, we have the axiom, neutral axiom, and anti-axiom, you know, respectively. So in this case now, we can see that all the elements, I mean, we can allow the elements, of course, now to behave, you know, naturally, okay? So that if you have a particular axiom, you may have some elements, of course, in that particular structure that we obey that, you know, that axiom or law. And you may have some elements that will not even obey, you know, the law or the axiom at all. And you see some that will partially obey and partially, you know, disobey the law. This is what this new direction, of course, now is now looking at. And then since Smanadache, of course, now, you know, introduced this one in 2019, people are taking it up, and a lot of research, of course, now, you know, is going on in this particular field. Okay, now let me give this definition very quickly. That we have a classical operation is an operation well defined for all the sets elements. This is what you have now for the classical structure. You know, for the, like, take a ring, for example. You know, distributivity, you know, associativity, and all those things, of course, now they are true for all the elements. Now, 2, we have a neutral operation. It's an operation partially well-defined, partially indeterminate, and partially outer-defined on the given set. So we may have an operation that is not completely, of course, now, you know, well-defined. It's partial. And even, of course, in some cases, of course, now it might be outright false. And that's what you have in number 3, which you call, of course, now an until operation. An until operation is an operation that is outer defined for all sets, you know, elements. And in 4, we define a classical law or axiom defined on an empty set is a law or axiom that is totally true. Okay, that is true for all the set elements. And this is exactly what you have now in the classical case, where all the laws, all the axioms, and everything, of course, now once, of course, now it is well defined on that particular set, then it is true for all the elements. So there is no room for partial, there is no room for falsity, and there's no room for, you know, completely false, you know, without anything. So this particular notion, of course, has taken care of those anomalies in the classical structure. So in this case, of course, now if you have a particular law, then that law, of course, now maybe partially, you know, obeyed, maybe totally, you know, disobeyed, and the combination of the two. Okay, then we have the definition of a neutral law. A neutral law or neutral axiom or philosophic law. So defined on the non-empty set is a law or axiom that is true for some sets elements, that is true for some and not true for some. And an anti-law or anti-axiom defined on a non-empty set is a law or axiom that is false for all the set elements. So once, of course, now you have classified as an anti-law. So definitely none of the elements, of course, now in that set will obey that particular law or axiom. And we have a neutral algebra. So it's an algebra that has at least one neutral operation or one neutral axiom that is true for some elements, indeterminate for other elements, and false for other elements. That is for, if you take a particular algebra, you know, once, of course, now it will be called a neutral algebra if it has at least one neutral operation. That's an operation that is partially true, you know, and partially false. Okay, that is true for some elements, indeterminate, that is, you cannot determine it now for some elements, and false for other elements. So a neutral algebra, of course, now is that. And an anti-algebra is an algebra endowed with at least one anti-operation or at least one anti-axiom. Okay, if you are talking of an anti-algebra, that is an algebra with at least one anti-operation. That is, there will be an operation that is not satisfied at all by all the elements. Okay, so, and then since Esmeralda, of course, now introduced this new structure. Okay, now we have done a lot of people are seriously working on this new area of research, and then now, in fact, recently, in fact, we have these new structures, of course, now being introduced. Okay, we have a neutral BE algebra, of course, now is now in the literature. Anti-B algebra is now in the literature. I have worked on neutral group. I have worked on anti-group, and I've also worked on the neutral ring. So all these are the areas where we have this new the new area of research. Okay, unlike, and you see the advantage of this particular direction is that what, if you look at the philosophic algebraic structure that we have studied, either the refined or the philosophic algebraic structures, that indeterminacy factor I is a problem. You will see that we have mentioned somewhere that the I, that is the philosophic indeterminacy I, you know, because of the fact that it is not invertible. If you raise I now to the power of -1, it does not, you know, it's not, it doesn't exist. So the I to the power of -1 does not exist. So therefore, it makes it very difficult for us now to do a kind of algebraic manipulations. For example, we know that in the classical group, you know, every element, you pick now from a group has an inverse. But because of the fact that you have I that is not invertible, once, of course, now you associate that I now with any element of the group, there is no way you can invert it. And that brings a lot of a problem. In fact, we have been trying to see how that I, of course, now that indeterminacy factor can be inverted. But up to date, of course, now we have not been able to get, the inverse of I, and therefore it is making it, of course, now very, very difficult, of course, now to do some algebraic manipulations and get some new structure. And that's the reason why most of the results that we have in the classical groups, are not holding in the either the Nielsen-Sophic algebraic structures or the refined Nielsen-Sophic algebraic structures, or even the hyper structures, because of that the I that is not invertible. All right. So I think we really need to know that very carefully. But with this new area of research just been introduced now by Smarandache, it is now very easy for you now, of course, now to work on the neutral, group. You can work on anti-group. You can work on the neutral, ring, the anti-ring, and things like that. All those ones, they are possible. Now, the concluding part of the paper is the new research areas in Nielsen-Sophic algebraic structures and hyperstructures, because it is this the notion of the neutral structures and anti-structures just being introduced now by Smarandache is very new, and the research area in that case, of course, now is still very virgin. So we are employing other researchers now to look into this. I have worked on the neutral group. I've worked on the anti-group. I've worked on the neutral ring, and the anti-ring. I'm presently working on the anti-ring. So these are the other areas where the researchers can also look at. For example, the anti-ring. Okay, so in this case now, just have to look at a particular ring in which at least a particular axiom is not satisfied, and it has been shown by Smarandache and another author that we have so many types of all these anti-rings, the anti-groups, all this. They've done that for the B algebra. They were able to show the number of the anti-B algebras. If you are given an algebra now, with some law and the axioms, they've been able to using some analysis now to show the number of either anti-ring, the anti-B algebra or the neutral B algebra that exists. And so that means I've got, for a particular structure, you can have so many types of such structure in the either anti or the neutral. So in this case now, I said, so the anti-ring, of course, now is still open for research, so people can still look into this area. And for the newcomers, of course, now into this, just look at the literature, see what we have done, and you can continue. So it's still very virgin. Of course, now it's open now for research. Now this one now for Nielsen-Sophic vector spaces. So we can also study this, all right, using the idea of what I've just explained. All what I just saying here is that unlike the normal vector spaces, whereby, of course, now you have the operation of addition and the scalar multiplication defined, and all these operations are holding for all the elements, of course, now in that particular vector space. So in this case, now it should not be. Okay, we are now looking at a situation whereby, some elements, of course, now we obey that law, whereas some will not obey the law, and some will not even obey it at all. It is not partial, so it's completely total. So this is the new area, of course, now we really want people, of course, to look at. Again, we have the anti-vector spaces. Okay, so this is also different now from the classical one, whereby all the laws, the axioms, are obeyed. So in anti-vector spaces, so this is it's a new structure whereby none of the axioms, and at least one of the axiom, is not obeyed. For example, it might just be that You know, for a vector space, if you call it V, the V plus is an abelian group. Okay. Now you can have an anti-vector space whereby for all the elements, V plus is not an abelian group. So in that case, now all other properties, of course, now may hold. But for that particular one, if it's not holding, then you must have had, you know, a structure called, you know, an anti-vector spaces. So the same thing, of course, now for the modules. So we can have the neutral modules. We all know the axioms laws now for the modules. So in this case, now what you are saying here is that what we are looking at a structure whereby, you know, some laws or some axioms of the modules are partially obeyed and, you know, partially disobeyed. Okay, and in that case, now we can also have so many, as I said before. So for all these structures, you know, this Mandati and one other author published recently using the complementary, you know, approach to determine the number of such structures that can be determined, and all this can be calculated, and we can see that. And so many researchers, of course, now can take, because I have worked on some of these types, and I can see that what each type of these, you know, space these structures, they have different structures, they have different properties. A property, of course, now we hold, you know, for a particular type, which of course now may not hold now for another type. So the researchers, of course, now we have to look at all these, you know, types or classes, you know, and bring out, you know, their peculiar properties. Okay, so the same thing, of course, now for the anti-modules. Okay, as I said, we all know all the law, the axioms of the modules. But in this case now, we are saying that we can bring out at least one of such axioms whereby none of the elements, of course, now will satisfy it. And once that can be established, then you have, you know, an anti-module. And as I said, there are so many classes, so many types of such anti-modules. Okay, so many of them. So therefore, this field is very open for research. People, of course, now can take each class, look at them, look at the properties, look at the structure, and you can also define a lot of the morphisms, you know. So of course, these are the areas, of course, now we can look at. That is, for all these types or the classes, can we have a morphism, you know, connecting the one or two classes? Okay, that is, if you have a particular class for an anti-module, and we also have another class, you know, also an anti-module, can we define a morphism? Okay, can a map that can connect the two together, that will preserve the operations, and that structure will still be there. So all these are new areas of research which people can really go into. Okay, and all those ones, of course, now are for the algebraic structures. Okay, but for the hyperstructures, okay, this is also open, which of course now I have not been looking at that. People, of course, now, you know, they are free, of course, now to look at those areas. For example, the neutral hypergroups. Okay, we know what is meant by an hypergroup. Okay, so for the hypergroup, of course, now in the classical sense, if you pick, you know, if you look at all the axioms of the hypergroups, you see all the elements of that particular hypergroup, of course, now we obey those laws. That is for the classical sense. But we are taking a paradigm shift now from that, whereby we now introduce the notion of the neutral hypergroups, whereby we look at a particular law or a particular axioms, okay, that is partially obeyed and is partially either partially true or partially false. Okay, and with that one, you can see we are going to have so many classes of such structures, and we can bring out so many properties, you know. And if you look at all these properties, if you look at all these classes very well, you will see that what they may have, of course, now a lot of you know, real life applications, because we are taking care of all the elements in a particular structure, you know, and we are considering the situation whereby, you know, they obey a particular law and they don't obey a particular law, you know, and all this, of course, now we find, you know, their applications in the real life cases. So, and little now for the anti-hypergroups. Okay, as I said, we all know the the axioms now for the law, guiding the hypergroups. But in this case now, we are saying that if you now want to, look at the anti-hypergroups, it means that we need to look for, a particular law that will not be obeyed, by all the elements, at least one. It might be more than one. Okay, look for at least one axiom or one particular, anti-operation or an anti-law that, all the that we hold for all the elements. Okay, for example, the productive axiom is one of the things, of course, for the hypergroup. Of course, it might be, you might have a situation whereby none of the elements, of course, now obey that particular, the productive axiom. And in that case, of course, now we now have an anti-hypergroup. And in that sense, as I said, we have so many classes of a such. And with that one, if you can look at all these classes, one by one, by different researchers, then we cannot look at what the mappings connecting all these hyperstructures. And from there, of course, now we can be talking of isomorphism and the rest, and the rest of them. And again, for the neutral hyperrings, okay, we all know what an hyperring is, okay, and then all the axioms, we all know the axiom of the hyperrings, all right. And therefore, so in this case now, we are looking at a structure whereby, a particular law, of course, now is, or a particular law or a particular axiom is either partially, or totally, either partially false or partially true. So in that sense, so we cannot have this new structure, which we call, of course, now the neutral, the hyperring. So we can look at the structure, you can look at the classes, and we can, find a way of trying to define the morphisms, of course, now between those structures and bring out their properties. And if you're able to do all this, as I said, we can have a lot of applications now to all this in the real life. So, which of course now those in the applied areas, of course, now can look at it, of course, and apply it to, so maybe computer science, humanities and things like that. Just like the forces set and the nutrosophic set of is been, logic is being applied in so many areas. And lastly, on the anti-hyperrings, okay, so can look at the hyperring, look at the structure of an hyperring, look at the axiom, look at the laws, and you now want to bring out at least one of those laws that cannot be satisfied now by all the elements, of course, now in that particular structure. So if, of course, that can be established, then you have a structure called, an anti-hyperrings. And as I said, there are so many types, so many classes of such, anti-hyperrings, and therefore they are going to have different properties. I have looked at, of course, now some classes of neutral group, and I've seen that, of course, now some properties that are true now for a particular class are not true now for a particular class, and some, of course, now are the same. Okay, and in that sense, of course, now we can be talking of how to find a relation between a particular class and another class. So this, of course, now will be the subject of research now for the listeners who are interested in this particular field. So, in summary of all that I've said, is that you have a classical structure. A classical structure, of course, now is a set with some operations defined on it. And once such operations are defined, then that all the elements of that particular structure we obey the law or the axioms. For example, the associativity, commutativity, distributivity, and so on and so forth like that. But there is no room for either some elements, belonging, obeying, a particular law, and some, of course, now will not obey the particular law. And you can see that's exactly what, of course, now what's happening in the reality. And if you recall, that's exactly what actually brought in the theory of the forces set introduced by Sade. Okay, because for the classical set, if you have a set X, it is either an element belong to a set or it does not belong to the set. Okay, so it is either you are there or you are not there. There is nothing in between, and for the first set, of course, now bridge that gap and allows, the element now to gradually belong to a particular set. An element, of course, now can belong to a set with grace of membership. Okay, but you can see the deficiencies of the forces set and the institutional forces set is what brought in, of course, now the the nutrosophic theory, brought in down by Smarandache. And we have been trying to see how that, that theory can be applied in the area of mathematics. I mean, in particular, the algebraic structures. I have been working on the algebraic structures, of course, now since this, I got to know of this particular new field of mathematics. Okay. And then you see this new area now, it's now a radical departure. Now, from if I even giving us, of course, like a kind of a relief, because I'll be having the problem of trying to find, for example, if I have X, if I have in the nullosophic ring of, let's say, integer modulo 2, okay, or integer modulo 3, and I have 2, yes, I have 2, 2i, 2, 2i, or you can write 2 plus 2i. How do I invert 2 plus 2i? It's a problem. Does not have inverse, and therefore, if you are not working on a group, if you are working on the nullosophic group, it means that you cannot easily, manipulate with inverses like we normally do now for the classical group. Ditto now for the fields, for the fields, all the elements must be invertible. But if you are not talking about the nullosophic field or defined nullosophic fields, the element there, we just call them, of course, now fields. The elements there, of course, they are not invertible because of that, the non-invertibility of the indeterminate factor I. Ditto now for the refined one, I1, I2. They don't have inverses, so therefore we have problems. But in these particular areas now, then you can see that everything, of course, now is now being brought together. So therefore we have a large latitude for us, of course, now to look at the structure of the algebraic structure, see, of course, now how we can bring out, of course, now their properties, and do a kind of manipulations. And of course, now this one, of course, now we have more real life applications than the other ones we have done in the past. So I think at this point, I really want to thank everybody for having me on this particular platform, giving me the opportunity to present this particular talk. So I thank you all now for your rapt attention. So my name is Professor Agboola, AAA of the Department of Mathematics, Federal University of Agriculture, Abeokuta, here in Nigeria. Thank you very much.
Participants, any queries?
سبقنا هذا باريش تسبق اسكت بركاش وسر بي بركاش
Participants, any queries?
Thanks a lot. Thanks. Hi, Dr. Adesina.
Yes, I'm listening.
Yes. Thanks a lot for the informative and excellent presentation on nullosophic structure. I want just to mention to participants that in the literature there are two nullosophic numbers. The first is called numerical nullosophic compounds based on the triad, trat, and determinacy and falsity, which this and the second is called the literal nullosophic number based on the number which equal E plus IB. So the two numbers are totally different and has many application dependent on the application context. So I want to thank you a lot for your presentation. Thanks.
Thank you very much.
This man.
Anybody? Anybody wants to clarify their doubts with the professor?
I want Dr. Adesina. I want to mention also to the participants that there are many articles of you published in the International Journal of Nutrosophic Science. If somebody wants a lot of information on your work, they can just see the website and upload the article and then read it carefully, and also they can work on your work. It's good. Thanks.
Thank you very much.
Thank you, sir.
Thank
you, sir. It's a very nice, excellent presentation. It is a very new idea, nutrosophic structures and all that. It is very, very new to us. Where can I obtain all those literature, sir? In the last area of research, have written so many areas. Is that research already done on that area, or is it available now?
Yes, there's a particular journal dedicated now for nutrosophic papers. You know, we have nutrosophic sets and systems. So it's available online, and all the papers there, of course, now they can be downloaded. The same thing, of course, now for the International Journal of Nutrosophic Science. You know, IGNS is also there. You know, just Google search it, you will see it, and all the papers we are talking about, they are all available there, and they can be downloaded. So all my papers, of course, now they are there, and they are free. They can be downloaded, and if you have any complaint or anything, then you can get back to me, of course, now through my emails. Thank you.
Thank you, sir.
Yeah.
Another information, Dr. Adesina, that you listen to me?
Yes, I'm listening.
Another information I want just to mention to the participants that Dr. Madeline, which in the same session will present another concept like the nutrosophic polygraph, polygraph, and etc. So I want all the participants to participate to her session, because it will enrich your works and other information on nutrosophic structures. Thanks.
Thank you, Dad, for that information.
Wonderful, sir.
Anybody has doubts?
Good afternoon, sir.
Yeah, thank you.
Good afternoon, sir.
Hello, I'm listening.
Yes, sir. Is it possible to extend the concept of intussusty fuzzy towards nutrosophic, sir?
So all what?
Is it possible, sir?
Is it possible to do what?
Oh, okay, sir. Okay, sir. What about picture fuzzy, sir?
You said, is it possible now to extend the nutrosophic theory to what?
Sir, in optimization techniques and statistical concepts like regression analysis, etc. Actually,
Yes,
I did
yes.
my.
Yeah, it's possible. In fact, Smadachi has even published books on the nutrosophic statistics. It's possible.
Oh, okay, sir. Okay, sir.
So, and all these are available. All these are available online. You can download them. In fact, there is a particular book written by Smadachi, on the nutrosophic statistics. So all the statistics, something, of course, they are containing there. So you can download them.
Okay, sir. Okay, sir. Thank you very much, sir. Thank you, sir.
Yeah, thank you very much.
Any more queries? Good evening, all. We are coming to the end of this session.
Dr. Adesina, I have just one question that some participants want to know. Is there any real application of notrosophic structure algebraic? Is there a real application from mathematics, for example, moving from mathematics to physics or other area? Is it possible or
Yes,
no?
yes, it's possible that, as I said, it is possible now to apply, and the people have even done in the they've done in the past. They've applied all this, of course, now to medical diagnosis, decision making, to physics, especially now the quantum physics. This particular theory has a lot of applications, of course, in quantum physics, and the Smaradachi and others, of course, now they've worked, extensively on this. In fact, those are the things, of course, now Professor Salama was saying yesterday. It has so many applications, just like we have for the forces set. This one is even more expanded, and it has a lot of applications in them in so many areas. In so many areas.
A very excellent presentation was given by Dr. Professor Agboola. He has given classical algebraic structures clearly with neat examples, neutrosophic algebraic structures, refined neutrosophic algebraic structures, neutrosophic algebraic hyperstructures, neutrosophic algebraic structures, and anti-algebraic structures, etc. So these concepts are very new to us, and we are very proud that we are one of the participants of this FDP. And thank you for your excellent presentation, Professor. And
Thank you very much,
Professor Bromi for his nice ideas. And I'll thank the participants for their patience listening. I thank our department colleagues and our convener, our HOD also. I thank one and all. Thank you very much.
Thank you. Bye-bye.
And one instruction for the participants. I thank Professor Agboola and Professor Syed Braumi. And I thank Syed Braumi for raising more queries in algebraic structure, and other participants who raised their doubts too. And tomorrow, a session between 11 a.m. to 12 a.m. in Indian Standard Time. And Professor K.N. Raghavan from Institute of Mathematical Science, Chennai, India, will deliver the lecture. Thank you.
Thank you very much. Bye-bye.
Thank you, Professor.
Yeah.
زوين سيدي الكونفيرنس الله يسوي.
Sorry, I beg your pardon.
Thanks, Dr. Barry, for the organization of this session. It is a very fruitful session. It contains a lot of information for participants. We will hope to organize another session on notrosophic theory for participants to provide them a lot of information on this new theory. Thanks.
Thank you, Professor. Soon we will have such workshop or webinar in neurosophic theory. Thank you for your kind words and for your encouraging too. Thank you, Professor Syed Braumi.
La mamá, pues le da mind blowing spelling.